So this is where we left off last time. Except for what's in the box is not really Maxwell's equations. What's in the box are the four equations that we learned in Physics 116. Of course, we didn't talk about Gauss's law for magnetism, probably. I don't remember, because it doesn't say a whole lot. But this is what we've learned so far. What Maxwell did is he recognized something really important here, something that I've already pointed out, that a changing magnetic field creates an electric field. So therefore, if a changing magnetic field creates an electric field, that means that really, if magnetic fields are really just a different way of looking at electric fields in terms, remember that a moving charge is a magnet, a stationary charge has an electric field, right? A moving charge has a magnetic field. So they're really, in a sense, magnetic and electric fields are really just different way of looking at the same thing. One in a moving frame of reference and one in a stationary frame of reference. Electric field is what a charge creates in a stationary frame of reference. A magnetic field is what a charge creates in a moving frame of reference. Frame of reference is really important here. We're going to have to probably just take a second and remind ourselves what we mean by frame of reference. Okay, I was going to give away a second there, that Maxwell recognized that a changing magnetic field creates an electric field. So what happens if you change an electric field? And that's not built into these equations. We'll come back to that in a second because we first need to talk about the frame of reference. So remember, FOR is frame of reference. And frame of reference is extremely important in physics. Really important idea. We talked about it almost on day one of Physics 115 when we talk about the fact that when we make measurements of position and velocity and acceleration, we make measurements relative to a coordinate axis, right? So our coordinate axis is our frame of reference, right? X equals 0. And that's our frame of reference. And the coordinate axis may be pinned to the lab, right? It's what's called the lab frame. May be pinned to a car if we're doing experiments in a car, which would be unusual, but we've certainly done that before. Or it may be pinned to the Earth. And then we have to realize, actually the Earth is moving, it's not stationary. So when we're doing experiments in the lab, are we doing experiments in a stationary frame of reference or a moving frame of reference? And we approximate it as a stationary frame of reference, but we have to understand, if we're doing really careful measurements, that it's actually a moving frame of reference. And then is the frame of reference moving at a constant velocity? Is it accelerating? Okay, those things are important. But remember, frame of reference. Frame of reference means we've got a coordinate axis and we're going to make our measurements relative to that coordinate axis. This is going to be really important for us in when we start talking about special relativity in particular. Understanding this concept of a frame of reference. So then you've got, right, again, we already said this, a moving frame of reference versus a stationary frame of reference. Perhaps we're pretending the lab is stationary, so that's our stationary frame of reference. Then somebody who's walking by the lab, they're in a moving frame of reference relative to us. But we can move into their frame, and now relative to the person walking by, the person within their frame, they're stationary, and the lab is moving by them. This is to do with relative motion, right? Is it the lab that's moving, or is it the person that's moving? You say, of course it's the person that's moving, but not necessarily, right? Because the lab itself is also moving. What if we held the person still and we moved the earth under them? I know it'd be a bit more difficult to do, but there's nothing that really says what is the absolute standing still frame of reference. It's not the Earth, because the Earth is both spinning about its axis, right? This is the Earth, it's spinning about its axis. It's also moving around the sun, right? The Earth is a moving frame of reference. So is the sun a stationary frame of reference? Well, I think we understand enough about astrophysics that we know that our solar system is in a galaxy that is moving around some center. Is it the center of the galaxy that's the absolute stationary frame of reference? Well, that's not clear either, because every galaxy is moving in the universe. And maybe there's a point somewhere in the universe, it's nowhere close to us, which is the absolute stationary frame of reference, but it becomes sort of meaningless to talk about a stationary frame of reference versus a moving frame of reference, an absolute stationary frame of reference. So instead, we just talk about relative motion. If we call the lab the stationary frame, then the car driving by is the moving frame. If you're sitting in a car, then in your point of view from where you're sitting, you're in a stationary frame, and the building is moving by you. That's a moving frame. It's all relative. And that's the idea behind relativity, is that's the first basic idea, is understanding relative motion. So what is an inertial frame of reference? Who remembers what an inertial frame of reference is, right? So inertial frame of reference. That is essential understanding, again, for special relativity. Give you a second to think about it. You should pause. You should try to remember. An inertial frame of reference, I'll tell you now, is a frame of reference that moves with constant velocity. And what does constant velocity mean? In a straight line at a constant speed. It does not accelerate, right? What's acceleration? Acceleration is a change in velocity. That's a change in speed or a change in direction. So an inertial frame of reference is one that moves at constant velocity. Now again, quick aside, there is no such thing as an inertial frame of reference on the Earth, because the Earth is rotating, so it's always accelerating. But we can approximate inertial frames of reference because we don't really notice the Earth's acceleration except in like big storms and various things like a Foucault pendulum. But so we can approximate inertial frames of reference. But the concept of an inertial frame of reference is essential to understand special relativity. It is one in which the frame of reference moves at constant velocity. Okay, now that's just reminding you about frames of reference. We're going to come back to that when we define special relativity. So let's go ahead and look at Maxwell's equations, come back to Maxwell's equations and say, well, if electricity and magnetism, the relationship between magnetic fields and electric fields really has to do with frame of reference, that means that a changing magnetic field, what's circled on the right, creating an electric field means that a changing electric field should also create a magnetic field. But that's not seen anywhere in these equations, so something must be missing. What Maxwell recognized is there is indeed something missing, and it's missing from Ampere's law. There's a term missing here. And and this is what Maxwell recognized, is that there's a term missing here. What Maxwell recognized, I'll try to do this real quick without going into a lot of detail. You'll just have to trust us that it makes sense in a physics world. But what Maxwell recognized is that there's a term missing here, and we call it the displacement current. It's actually looks like mu0 ID. Let me fix this. So I haven't explained what Maxwell's displacement current is yet, but what Maxwell recognizes is that there's a term missing here. And this ID current, is called displacement current, has to do with changing electric fields. And so now Ampere's law is called modified Ampere's law, or Ampere's law modified by Maxwell. Sometimes it's still just called Ampere's law, but with this little extra mu0 ID, we can think of it as the modified Ampere's law.